If you are also looking for professional certified structural engineering services or courses, then don't forget to check link in description of this video.
Hey guys, welcome back to another tutorial, and in this tutorial we are going to discuss about wind loading as per ASCE 716, and we will be focusing on wind loading procedure for a directional procedure for main wind force resisting system. And I will be showing you how to calculate the wind pressure manually for your portal frame, and then you can apply over it as per ASCE 716. So if we talk about ASCE 716 and particularly regarding wind, so these are the chapters of ASCE 716 regarding wind. And as far as we are concerned, so we will be focusing on chapter 26 and chapter 27, as chapter 26 is basically the general requirements that we need for calculating the wind pressure, and the procedure that we will be following is directional procedure that is applicable for the building of all heights. So that's why chapter 26 and chapter 27 are useful for us. So the very first thing that I will do, first I will give you the overview of chapter 27, that's the directional procedure overview, that what are the steps, and then I'll explain you those steps, and then we will be moving towards calculating the wind pressure for our portal frame. So let's start with the steps for directional procedure. So these are the steps that you can see on your screen that we follow for calculating the wind pressure. The very first step is we have to determine the risk category of our building, and we have to determine the risk category from this table 1.51. And how we select the risk category of our building? We select the risk category of our building based on the occupancy and the risk category. Based on that, we select the risk category of our building. That's the very first thing. Then the next thing is we have to determine the basic wind speed. Now as far as US is concerned, so for US the maps are given in ASCE 716, so you have to go and check out your code and see what is the wind speed for your locality in which your portal frame is located. The next step is, okay, so that is, here it is, wind hazard map. And then if we go to next step, that is step 3, determine the wind load parameters. Now if I talk about wind load parameters, so the very first parameter is wind directionality factor. So let's go and see what do we mean by wind directionality factor. So it can be determined from this table 26.6 of ASCE 716, and based on your structure type, you are going to select this wind directionality factor. Okay, I will be showcasing you we will be coming back to again this when we will be seeing our structure for which we will be calculating our wind pressure. So based on structure type, you select the wind directionality factor. Then topographic factor. Now this factor we usually take 1 until and unless if you have any building that is located on any hill. If you have your structure located on hill, yeah, so this is topographic factor, that is KZT. If your structure is not located on hill or ridge or escarpment, then you can take this value as 1. Otherwise you have to calculate this value as per code procedure which is written over here. As far as our structure will be concerned, we will not be having a structure that will be located on escarpment or ridge or hills or ridges, so we will be not calculating this value. We will be just taking this value as KZT equal to 1. So then comes the ground elevation factor. Now if I talk about ground elevation factor, so it depends on your height. Okay, what is your ground elevation above the sea level, and then based on that you select this ground elevation factor. The conservative approximation KE equal to 1 is permitted in all cases. So if you don't know your ground elevation above sea level, you can just simply take this value as KE equal to 1. Then comes the gust effect factor. Now if your building is rigid, so you are permitted to take gust effect factor as 0.85. That's what the code says. The gust effect factor for a rigid building or other structures permit to be taken as 0.85. Now these parameters will be quite useful while calculating the wind pressure, which I will be showing you in a while. Then enclosure classification. Now see, we have three types of enclosure. The very first is open building, then is partially enclosed, and the third is enclosed. So let's look at them one by one, what these enclosure definitions mean. So the very first enclosure classification is building enclosed. Now, how do you say the building is enclosed? In simple words, it means if each wall of your building has area of opening less than 4 square feet, then that building will be called as enclosed building. Each wall has an area of opening less than 4 square feet. That building will be called as enclosed building. Or there is other criteria. If each wall has area of opening less than 1% of the total area of the wall, then again this criteria is satisfied, then your building will be called as enclosed building. The next is open building. If each wall of the building has more than 80% of opening, then your building will be called as open building. The third is partially enclosed building. Now, to be partially enclosed, it needs to satisfy both these conditions, that is 1 and 2. The very first condition is the total area of opening should be, it exceed the sum of the area of total openings in other parts of the structure, means walls and roof. If your particular wall has opening such large that if we compare its area with all other areas, with all other opening areas of your building, and that wall area is 10% more than those all combined area, then this is the very first condition for building to be partially enclosed. Means any particular your wall should have area of opening more than 10% of the total area of opening in a building. That's your first criteria. The second criteria is that if your opening in a wall is greater than 4 square feet of 1% area of the total wall, and the total area of other openings in a structure does not exceed the more than 20%. Simple words, the second condition is if your area of opening in a wall is greater than 4 square feet and is greater than 1% of the total area of the wall. Along with that, the total area of opening in other part of the structure, if we combine all those openings, so they should not be, the percentage of opening should not exceed 20% of the building envelope. So that's the two conditions that should be satisfied for building to be partially enclosed. Then comes so these were the classification based on enclosure classification. Okay, then internal pressure coefficient. Now we have positive internal pressure as well as negative internal pressure, for which we have to see section 26.1.3. Basically, this is dependent on your enclosure classification. Internal pressure coefficient is dependent on your enclosure classification. So as per your enclosure classification, you select your internal pressure coefficient from this table of the table 26.13 of ASCE 716. The next is we have to determine the velocity pressure. Sorry, before that we have to determine the velocity pressure exposure coefficient, KZ or KH. Now as far as this KZ or KH is concerned, so let's go and see. So KZ and KH, Yeah, here you can see this kz or kh. Now what do we mean by kz or kh? First let me explain you that. See, as far as windward side is concerned, so you must know this thing. Before coming to that, let me tell you what do you mean by windward side and what do we mean by leeward side. So I will go back to my structure. See, if here you can see, if the direction from which your wind is coming, that direction will be called as windward side, and the direction opposite to that windward side will be called as leeward side, and the adjacent side will be called as side walls. Now if this was the case, if your wind is coming from there, so this direction will be called as windward side, opposite to that will be called as leeward side, and the adjacent side will be called as side walls. And do remember this thing. Now if wind would be coming from this side, now this will be windward side, the adjacent will be side walls, and the opposite to it will be leeward side. Now as far as windward side is concerned, so in windward side the pressure is applied in a trapezoidal manner, means at each height the pressure is varying. Now since at each height the pressure is varying, and that is due to this thing, kz factor. So kz means for windward side, and kz means that at each height you calculate pressure. That will be for this kz will be used in calculating pressure for the windward side, and kh means the pressure at this kh will be used for calculating the pressure at mean roof height. Okay, and we select this factor based on the height and exposure category. So now first we should understand what do we mean by exposure category. Now if I talk about this exposure category, so it depends on your surface roughness. That's the very first thing on which it depends, and the next thing is your building height. Okay, so the very first thing that we need to understand is surface roughness. So we have surface roughness B, surface roughness C, surface roughness D. So what do you mean by surface roughness B? Urban and suburban areas. So you can go and read out this and see. And basically if I explain you in simple words what do we mean by the surface roughness, it shows us the locality of where your site is located. So what are the localities of your site, in which your site is located? Because if let's say your building is located in such region in which there are a lot of other buildings, so in this way there will be not much wind pressure, because wind coming to your structure will already be obstructed by other structures. Okay, the next thing is, and which I think so comes into the category of surface roughness B. And the next is, let's say your building is located in such region where there is no any other building which can obstruct, or any other obstruction that can obstruct the wind pressure. So there much amount of wind pressure will be coming to your building. So that will be like surface roughness D. So this is what is mean by surface roughness. Now we select the exposure category based on exposure category, which will lead us to decide the kz or kh factor. And for selecting the exposure category, we need to know the roughness of our roughness near our building. So this is, if here what does the code says? Code says that you should check you should check for exposure category B and exposure category D. And if your building does not fall into the category of exposure category B or D, then exposure C shall be applied for all cases where exposure B or D does not apply. So first we need to know that what do we mean by exposure B category and what do we mean by exposure D category. So for exposure B category, if this condition is satisfied, if your roughness is B and this condition is satisfied, then your exposure category will be B. Or if this condition is not satisfied and either of these, any condition is satisfied, then your surface category, your exposure category will be D. And if these both does not satisfy, then your exposure category will be C. So exposure category basically depends on the surface roughness. And what do we mean by surface roughness? Surface roughness we mean at which locality our building is located. So it's like all the things are connected. If we need KH or KZ factor, we need to have exposure category, because exposure category and that exposure category depends on surface roughness. And what do you mean by surface roughness? I've already explained you. So this is how you select your KZ or KH factor. And I already told you this KZ factor, since you for windward side you calculate the KZ at multiple heights along the height of the building. So that's why this at every height you select the different value of KZ. But for leeward or side walls you select just one value at mean roof height. Now the next thing is velocity pressure coefficient. Exposure coefficient we have calculated. Velocity pressure, let us see this velocity pressure, QZ or QH. So this is the formula that code gave us for calculating the velocity pressure. So see here, so far whatever parameter we have discussed, all are mentioned over there, and we will be using this formula because we are having our speed in miles per hour. So KZ, I already told you, it's velocity pressure exposure coefficient, just now we discussed. Then KZT is topographic factor. It can be taken as equal to 1 if your building is not located. It can be taken as equal to, I don't know, I think let us take is let us go and check what its value should be taken if your building is not located in any, if site condition if site condition and location of buildings in other structure do not meet all the conditions specified in this, then you can take as KZT equal to 1. Okay, so that is the thing, that if your site is not on hill or any ridge, you can take this value as 1 KZT. Then KD is directionality factor, which I already showed you. If you go back and see, so based on your building type structure, you select this KD factor, directionality factor. Then KE is your elevation factor. It can be conservatively taken as 1 if you don't know what is your height of building above sea level. And V is your wind speed. Now the only thing that is remaining is how we determine the external pressure coefficient, and then how we ultimately calculate the wind pressure. So as far as external pressure coefficient is concerned, so this is the table that has been given to us in the code. I will be showing you how to use this table when we will be implying this ASCE 716 on our structure portal frame. So let's move to our next task, that is applying this ASCE 716 on our portal frame. So guys, this is the structure on which we have to apply our wind loading as per ASCE 716. This example I have taken from ASCE 710 reference book on wind load, and I will be applying 716 procedure on this example. So first let's understand our structure, and then we will be moving forward. So as far as our structure is concerned, that is portal frame, it's 250 feet long, 200 feet wide, its eave height is 20 feet, and its ridge height has not been given to us, but the slope has been given to us, so we can easily calculate this ridge height. So it comes out to be the length of the shed 250 feet, the width of the shed 200 feet, eave height comes out to be 20. Using that slope, we calculated the ridge height, that comes out to be 53.3 feet. Basically you get the vertical, then you add 20 into it, then you get ridge height 53.3. The angle again we calculated from that slope. So that was all about the structure. Now how we will be applying, our basic ultimate goal is to apply the wind pressure. Now as far as wind pressure is concerned, so we will be using this formula, as because our building is enclosed building, so we will be using this formula for calculating the wind pressure. Now what terms does it contain, we will discuss it, But before that, let me tell you one quite important thing, that is the wind can either flow now this is your ridge, no? Here you can see this is your ridge. Now wind can flow mainly in two directions. The very first direction is normal to ridge, that is this direction, left right. Other is parallel to ridge, that is north south direction. Okay, so the wind can mainly flow in these two directions: parallel to ridge, normal to ridge. Now the next important thing that I need to tell you over here is the side from which the wind is flowing, the side from which the wind is coming, that side will be called as windward side, and the side opposite to that will be called as leeward side, and the adjacent side will be called as side walls. Let's say if your wind is flowing in this direction, okay, so what will happen, this direction will be windward, opposite to it will be leeward, and the adjacent will be side walls. So windward, leeward and side walls. Adjacent will be side walls, opposite to it will be leeward, and the direction from which wind is coming will be called as windward. Now the next thing is that we should understand that, see, we will get the wind pressure using this formula, and I will show you how do we get the wind pressure using this formula. But before that, now once we get our wind pressure formula, so what does the code says that how should we apply it? So the code gives us these 4 load cases in which we should apply the wind load on our structure, on our portal frame. Okay, and on which see, as far as portal frame is concerned, so it's the columns that will be taking the wind pressure. So I will be applying the wind pressure, that will be basically the wind pressure is in PSF, okay, and I multiply it with the tributary width of the columns and tributary width of this bay, and then what I do, I apply it. But that's the thing I will tell you later on in this video. But before that, the thing I was telling you, the code says that we have to apply in these 4 load cases, and it is not necessary that we should consider all those 4 cases. That's what the code says. So the code says, here I have written in easy words that what does the code says. So the code says all building must be checked for the 4 wind load cases from this figure. Here you can see. However, there is an exception that allows skipping the torsional cases, that is case 2 and 4. This one, case 2 and case 4, if the building meet appendix D requirements. Okay, if the building meets the appendix, you go and check out the ASCE 716 code and that appendix 6. If your building is meeting that requirement, then you can skip this case 2 and case 4. As far as our portal frame is concerned, so we have got our mean roof height of 36.7 and length to breadth ratio is 0.8. So we check section D.6.4 case D, which applies to class 1 and class 2 simple diaphragm building with height less than 160 feet and length to breadth ratio between 0.5 and 2. So our building qualifies for this category because our rigid frame is spanning 200 feet, and so based on our structure configuration, we are permitted to leave this case 2 and case 4. And since our structure is quite symmetrical, so instead of even going for case 3, we can just consider case 1 as well. But code recommends us to go for both of these cases, and we can exclude this. So now we came to know that how we can apply the wind pressure in load cases to our structure. Now let's first understand how we calculate this wind pressure, and then I will be telling you how you can apply it to your portal frame. So if you look at this formula, in this Q is U. Q is what? This is the velocity pressure. Okay, so this is let me show you velocity pressure. So see, this is the Q. Q is what? Your velocity pressure. Now what do you mean by QZ and what do you mean by QH? I will be telling you, wait a while. So Q is your velocity pressure, and if it's QZ, so it means it's for windward wall, and you do not get just apply one value of Q and apply throughout the whole height of the building. You calculate it segment wise because it's a trapezoidal load, not a UDL. Then QH is for leeward. So leeward and side walls or roof, they will be applied uniformly distributed load. Okay, Q will be in UDL form, but for windward wall it will be in trapezoidal, that is QZ and QH. Then G is your gust factor, CP is your external pressure coefficient, and GCPI is your internal pressure coefficient. Then now let's go and see the other factors. So see, this is the other data that we have to consider. Our basic spent weight that has been given to me is 150 mph. Risk category is 2. Mean roof height is that we calculated from average of ridge and eave height comes out to be 36. Feet. Exposure category is C. I have already explained you how do you get the exposure category. Then KZT factor is 1 because our structure is not located on any sort of hill or ridge. Then KD is 0.85 based on our structure. Then gust effect factor is 0.85. I already told you how we select these factors. And enclosure is closed. And based on this enclosure category, our positive internal pressure comes out to be 0.18 and negative internal pressure comes out to be minus 0.18. And value of KZ, so whatever is given in this formula, we have already defined here. But we have not defined KZ factor because this KZ factor depends on the height. So this is the formula for velocity pressure that code gave us, and for getting this Q value we need KZ. Right now we haven't evaluated its value, we will evaluate it, but KZT we know, KD we know, and speed we know. So the next thing is value of KZ are obtained based on the exposure category and height of the building. So KZ depends upon the exposure category and height of the building. That's what we have seen in the code. Here you can see based on your exposure category and your height of the building, you select the KZ value. Now the thing is that, let's come back to our example. So far we knew about KZT, KD, V. The only thing that was remaining KZ. And here you can see we have evaluated the expression of QZ, but it is in the form of KZ. Now, as I told you, as I have shown you, that the KZ depends on your height, and based on height, it has got different values. Now, the important thing that I need to tell you over here is, if you are calculating the wind pressure or velocity, let's say velocity pressure for leeward side, for either for leeward side or roof or side walls, you do not need to get the KZ value at every height. You just need the KZ value at roof mean height. That's all. Nothing more than that. But as I mentioned earlier, when you are calculating the wind pressure, or let's say velocity pressure for your windward side, then you need to get the KZ value at different heights, because as far as our windward side is concerned, so here you can see the pressure is applied not in the form of a uniformly distributed load, but a varying load. That's the thing. That's why we take the value of KZ at different heights. Now the next thing that is remaining for us is external pressure coefficient, because we have already seen that we get the value of internal pressure coefficient from this enclosure classification. Since our building is enclosed, therefore internal pressure coefficient is plus 0.18 and minus 0.18. So external pressure coefficient. Now the external pressure coefficient is different for walls and different for roofs. So let's go to the code and try to understand it. So see, here you can see this is the table that code gave us if we want the external pressure coefficient for walls. The code says for windward walls, at any case you have to take the value as 0.8. For side walls you have to take the value of minus 0.7. But for leeward side, your CP value, that is your external pressure coefficient for walls, depends on your L over B ratio. And even this L over B ratio varies depending from where your wind is coming. If your wind is coming from let's say, if your wind is normal to ridge, then you will have different value of L over B ratio, and if your wind is parallel to ridge, then you will have different value of L over B ratio. That's what I am going to show you right now. So this is for external pressure coefficient for walls. We will be discussing roof and roof, but later on. First, let us understand this wall external pressure coefficient. So let's go back to our example. So here you can see the pressure coefficient for the windward wall and for the side walls are 0.8 and minus 0.7 respectively for all L over B ratio. But the leeward wall pressure coefficient is a function of L over B ratio. For wind normal to ridge, the wind that is coming normal to ridge means the wind that is coming from, this is your ridge, normal to ridge means wind that is coming from this side, from left or right. So for wind normal to ridge, L over B ratio is 0.8. Therefore the leeward wall pressure will be how much? So let's go to the code. 0.8. Since 0.8 is between 0 and 1, therefore it will be minus 0.5. Your CP value will be minus 0.5. Here you can see CP value minus 0.5. Now for parallel to ridge, our L over B ratio is 1.25. So the code does not give us any, the 1.25. So since there is no clear instruction about 1.25, so what we gonna do, we gonna interpolate it, and by using interpolation we get this value minus 0.45. Then for side wall minus 0.7. So this was how we get the value of external pressure coefficient for wall. So guys, now let's look at how do we get the external pressure coefficient for roofs. So the code tells us to use these two tables for calculating the roof pressure coefficient, roof external pressure coefficient. And this table we have to use, the very first table we have to use when our wind is flowing normal to ridge and our theta is greater than 10 degree. So in our example, we are in this case for normal to ridge and our theta is greater than 10 degree. So we are going to use this table for normal to ridge, and this second table we are going to use when our wind is flowing parallel to ridge. So for normal to ridge, use this table, and for parallel to ridge we will be using this table. And if our theta would have been less than 10, so then even for normal to ridge we will be using this table. So we will be just sticking to one table when our theta will be less than 10, and that is the second table. But if your theta is greater than equal to 10 degree, then for normal to ridge use this table. For parallel to ridge, use this value, use this table. Now let's see as far as our theta is concerned. So it comes out between 15 and 20 degree. So we will interpolate its value for theta, basically because our theta is how much? It's 18.4 degree. So therefore you can see for windward roof we have interpolated its value for windward side. Similarly for leeward side we will again interpolate its value. Now the important thing here you need to see is that for windward side we are getting two values of external pressure coefficient. So it means, what does it mean? It means earlier, see, we were calculating the net pressure with positive external pressure and negative external pressure. Okay, two pressure values. Now for roof of when the wind is flowing normal to ridge, and for our roof we will be having four values of pressure. That's the important thing that you should keep in your mind. Okay, so this was about how does we take out the value from external pressure coefficient for roof from the code. Similarly, For the parallel to ridge, based on our H over L ratio, we get the value of Cp. And here again, this 0 to H over 2 is basically your distance from your windward edge. So from 0 to H over 2, from windward, you have to use this Cp coefficient. For H over then from H over 2 to H, you have to use this. Basically, this is the distance from windward edge. So let's go back to our example. So here you can see external roof pressure coefficient for wind normal to ridge. For the roof angle of 18.4 degree, we get these two values of external pressure coefficient for windward. For leeward roof, see, if this is your windward side, this is your windward roof, this is your leeward roof. Okay, so for windward roof you get these value, for leeward roof you get this value. Then for wind parallel to ridge, so basically here it has not been shown, but it has directly been included over here. So now we are all set to do all our calculation. So let's go and put all the values in this formula and get our net pressure. So here you can see this calculation has been shown over here for wind normal to ridge. As I told you earlier, for wind normal to ridge, for windward side, we do not apply the value as one value. We apply as a UVL, not as a UDL. So therefore, at 0 to 15 height, we have calculated one values, and then the other values I have calculated is at 20. Now here is an important, interesting thing that you need to know. You need to note is that see, we have just gone up to 20 feet. Why? Because as far as our wall normal to ridge is concerned, so its height is just 20 feet. But as far as our wall parallel to ridge is concerned, so its height is up to 53.3 feet. Okay, so that's the important thing that you should keep in your mind. So you get based on this Z value, you calculate your Q value. I already showed you how you calculate this Q value over here. The only thing that was missing over here was KZ, and I showed you how you get the KZ value at different heights. So you get, in this way you get your Q values. Then G, gust factor, CP, external pressure coefficient, just right now I have explained you how do you get it. Then this is your positive, and then finally what is this? This is your net pressure that you calculate from this equation. So everything you know you need for calculating the net pressure is given, and you just substitute the value and you calculate the net pressure, positive net pressure and negative net pressure, with positive internal pressure, net pressure with positive internal pressure, and net pressure with negative internal pressure. Now let's come to when our wind is flowing parallel to ridge. So here you can see when our wind is flowing parallel to ridge, so we calculate the up to 53.3 in the similar way. Then for leeward wall, then side walls and roofs. Now here is a quite important thing that you need to know, that see, where it is. Yes. So see, you might be thinking that whether I should use minus 0.9 or minus 0.18 value. So it depends on your situation. You have to use the largest section value, that is 0.9 or 0.5 or 0.3 for checking roof connection and hold downs, okay? And check the smaller section value, that is minus 0.18, when combining wind with snow or live load. If the project has no snow load or minimal roof live load, then you have to use minus 0.18 value. Then if the project has no snow load or minimal roof live load, then this value minus 0.18 will rarely govern, so it means it will not be considered, but it should still be verified rather than simply ignored. So most of the time we will be taking this greater value, that is minus 0.9, minus 0.5, minus 0.3 at these location from the windward edge. But if this should be checked, so use the larger section value for checking roof connection and hold downs. Check smaller section value when combining wind with snow or live load. Okay, if the project has no snow load or minimal roof live load, then this minus 0.18 can be ignored. So guys, that was all for today. I have explained you how do you get your pressure values. Now as far as applying is concerned, so simply what you need to do, you just need to calculate the tributary width and apply as a lateral load on this columns. So in this way you can apply wind loading for your portal frame as per ASCE 716.